First off, I wanted to say to everybody that it's been a real joy to teach you guys. I'm glad you were in this class. And now we'll go through a review of everything and any questions or anything that I neglected to say, which I probably told too many stories. But first, maybe we should just go through a review of the basic stuff. Okay, so first week, remember we talked about not only the history of recording arts, but we also talked about what's typically in a recording studio. There is a control room where the equipment is and the engineer is and the speakers. There's a live room, or a studio room they call it, where the musicians stand and play, or the piano's out there, and that's where the music's created pretty much. And then there's sometimes in the larger studios they have what's called a machine room, and the machine room is special because it's really geared to keep all of the equipment in. So it's got its own separate air conditioning and maybe electrical system because the equipment gets hot, and all the fans on all the amplifiers and the computers and all that. You don't want to create more noise in the listening environment. And of course, you got to remember there's always a lounge of some sort, right? That's a fun place to be. But anyway, so those are the main elements of a recording studio. So obviously the control room is where the equipment is, where the critical listening environment is, where the engineer, producer, and the people that are recording, sometimes the record label people, sit in. They have small speakers, sometimes large speakers. The large speakers are really great to get excitement going because you can listen loud. You've got a board generally. You've got other equipment, outboard gear if necessary, mostly computers these days. And in the live room, as I mentioned, you've sometimes got a drum kit, a piano, all of where the musicians are, where the musicians stand or sit and play together. And as I mentioned, the reasons for having a machine room, it's really handy to have it if you've got the real estate to do it. Most of it has to do with heat and electricity. So if you've got a separate electrical system feeding all of your critical gear like your computers, in one of the studios I worked in, we had a car battery pack that cost like $20,000. It had to be 18 car batteries. If we had a power outage, it would keep the power going for 10 minutes so that we could shut everything down safely and back everything up. Because if you have a power outage, which happens in Los Angeles, you get these brownouts where people are running their air conditioners and the voltage drops too low because of the usage of power, and then the computer freaks out and shuts down sometimes in the middle of something you're doing. And if you're working on a serious project, you just can't afford to lose the data. That brings me around to always saying back up every second. It's so automatic for me. Whenever I do something, I back it up without even thinking. That's why a machine room is important. The other reason, not just for the electrical system, but also it's really important for the air conditioning system, because all of the computers and all of the amplifiers and all the equipment generates heat. And so if you had it in the control room and you kept the control room cool enough so that the equipment wouldn't get too hot. Sometimes it's too cold in the control room. Every day, whether it's 100 degrees outside or whether it's 50 degrees outside, it's freezing all the time in the control room to keep all the equipment cool. The other issue is if you have one air conditioning system that feeds the studio room and the control room, if the control room's comfortable, the studio room is like icicles. And if it's comfortable where the musicians are standing, then the control room's too hot. So studios generally have separate air conditioning systems, and it's really great to be able to get the heat-generating equipment out of the control room. Then you can specially insulate it to keep it cool and have a separate air conditioner for it. We also talked about the basics of sound. We talked about wavelength. Wavelength is the length of a wave, one cycle of a wave, a periodic wave. So you think of a sine wave. So wherever it crosses the axis, the next time it crosses the axis is one cycle, and the length of that is a wavelength. The amplitude is how high it is and how low it goes. We talked about what frequency is based upon the speed of sound and the wavelength. Frequency is equal to the speed of sound divided by the wavelength. And we discussed the fact that low frequencies, and I think I gave you an example of 40 hertz, which is like the sub bottom end of a kick drum or a bass instrument, is like 28 feet long or 28 and a half feet long. So it's a very long wavelength. For one cycle to progress is 28 feet, where if you look at 5 kilohertz, which is right in the audible region of my voice, the high end of my voice, where diction happens, is at like 2K to 5K, it's like 2/10 of a foot. So maybe like 2 inches long. Just in general, just remembering that the wavelength varies from very small to very large in terms of the frequencies. Going down, it's very, very long. Going up to we can hear up to 20,000 hertz. So the wavelength of 20,000 hertz is very, very small. And that sort of ties into the fact that low frequencies need more energy to produce the wave because it's such a long wavelength. You have to have enough energy to move air 28 feet for one cycle, where high frequencies don't need a lot of energy because they're very small disturbances in the air. That's why a tweeter's small and a woofer's large. You have to move a lot of air for a woofer, and a tweeter, you only have to have a small disturbance in the air. So that stands to reason that high frequencies carry less energy and low frequencies carry more energy. Also, low frequencies and high frequencies have another characteristic. Talked about hearing in the third week. I'll jump ahead. We talked about how you can determine directionality of sound. How I know something's coming from my left or from my right has to do with my two ears calculating the phase difference and the time difference from the sound hitting one ear and then going to the next ear. There will be a time delay because the speed of sound is fairly constant in air. A low frequency wave, if it's 28 feet long, the difference in the phase of where it's at between one ear and the next is relatively insignificant. But high frequencies, say 5 kilohertz, the phase is going to be totally different between my ears. My ears are maybe 8 inches apart. The physical length of the wave determines the fact that we can tell directionality in high frequencies but not in low frequencies. If my head was wider, I could hear directionality to a lower frequency range. But when it gets to be low enough, at some point I lose directionality. And you remember that because in a stereo system or a system in a club, they've got a subwoofer system, and it's never stereo. It's always mono, and it's placed anywhere in the room because you don't know where the bottom end subs are coming from. They just fill the room up. A theater system, same way. They can put the subs anywhere, and it doesn't really matter because you can't tell where that's really coming from. We talked about sine waves, and we talked a little bit about electrical characteristics. One of the laws that's really important to remember is Ohm's law. Voltage equals current times resistance. That little mnemonic device where you've got V over, let me draw it. You've got V over current, which is I, R, and you cover up the one that you want to find. So if you want to find resistance, you divide voltage by current. And Power's law. Power is measured in watts. Power is equal to voltage times current. So current is in amperes, resistance is in ohms, voltage is in volts. So you can basically calculate quite a bit of information that way. It's a very simple relationship. You can compare it to a water hose with water flowing through a hose, and the resistance, if the hose narrows, would be like a resistance to current flow. The pressure that pushes the water through the hose from your spigot is actually like voltage in a similar way, and how much water flows is actually like current. It's a really great sort of way of thinking of it because it's fairly consistent with what electron flow is like in a wire. We talked about phase of sound waves. So if you've got two identical sound waves and their phase is always in comparison to one another, you need two waves to compare to each other to determine what the phase difference is. So you need one as a reference. The other one basically represents how much time it's either late or early compared to the first one. 180 degrees out of phase of a sine wave means that it's going to cancel each other out because they're going to be opposite. When one is going up, the other one's going down. If it's 360 degrees, then they're going to reinforce each other and become double the amplitude. If it's 0 degrees out of phase, they're in perfect synchronization with each other. If you add them together, they're going to double the amplitude. We talked about speaker placement, and the best place to put speakers in your project studio or any studio is in an equilateral triangle where your head and your ears are at one of the corners of the triangle. And the reason that that's the best place to listen is because you get equal energy from both speakers hitting your ears at the same time. if you were off the center of that equilateral triangle, then sound would have a shorter path from one speaker than the other, and the sound would arrive at one ear earlier than the other ear. And we talked about how sound takes time to travel. That's a real important axiomatic principle. And it's not so fast that it's considered instantaneous. It really causes a lot of these things that we talked about to happen, like delays, phasings, reverbs, flanging. All of those kinds of things are developed because sound takes time to travel in a large enclosure. If it was as fast as light, we'd never have those properties. And we need to have, for our brain to determine delays, there has to be a certain amount of time passing before we hear the second iteration of a delay. We talked about what transducers are. The whole studio is full of transducers. That's really what recording arts is. Taking sound and acoustic energy and transducing it through a microphone into electrical energy, sometimes through magnetism, sometimes not. In a condenser mic, there's no magnetism involved. It's all electrical characteristics. But in a dynamic mic, you're using magnetism and the fact that you can move a coil through a magnetic field to create some little current flow. And that's how the dynamic microphone works. And the ribbon microphone works the same way. A condenser mic actually works on charge principle, but they all are transducers, and everything in our lives are transducers pretty much. I mean, the speaker is a transducer. It takes electrical energy, creates kinetic energy, and creates an air disturbance, which turns out to be acoustic energy. So what's another transducer? My human body is a transducer. I had breakfast this morning, and I turned it into chemical energy and motion energy and heat energy in my body. So I'm changing one form of energy to another, and that's the definitional part of what a transducer is. There's three basic sound waves we talked about: periodic sound waves, impulse sound waves, and noise. We also talked about the two different descriptions of a sound event, one being the frequency domain description, which involves a fundamental principle is that any complex wave could be created by adding together component sine waves and cosine waves at different frequencies, amplitudes, and phases to create any complex wave. And from that, you get the fundamental frequency, which is the lowest in that series of simple sine waves that add together to make the complex wave. And above that are all the harmonics. The harmonics and the fundamental have a couple properties that are important. The fundamental is always the loudest in the sound, and it's always tells the listener what pitch information. Harmonic structure, on the other hand, is an endless series of sine waves that decrease in volume, and they even go higher than our hearing can go. But all added together, they give the listener the quality of the sound. That's why we can hear the difference between middle C on a piano and middle C on a guitar, and know that they're different instruments because of the harmonic structure. That's how we can tell the difference between middle C on one acoustic guitar and middle C on a different acoustic guitar, because it has a little different harmonic structure. And voices, everybody's uniquely different because we all have different resonating cavities that create the harmonic structure. So that's why my voice sounds like it sounds, and your voices sound the way it sounds. So that's important to understand the qualities of what the fundamental means, what it means, and what the qualities that it carries for the listener, and also what the harmonic structure is and what properties it has. Another way to look at a sound event is in the time domain, which would be an envelope. And there's the attack on the envelope. If you look at an envelope from left to right in time, first thing that happens is you get an attack, then you get decay, and then you get sustain, and then you get release. Those four basic parts of the envelope are really important. And the interesting thing about it, I've always thought this was fascinating, is that if you change the envelope by using a compressor or an EQ or whatever process you want to go through, you actually change what the harmonic content of the sound is. And if you change the harmonic content, you actually change what the envelope looks like. Those two are linked. And so it really makes you realize that you're talking about a sound event, and these are just two descriptions of it.